Hi, since my internet is not great today, what I'm going to do is I'm going to record few specific topics of the chapter of measurements, and we are going to discuss all of that live in the class hours today itself. So what you need to do is you need to do the questions along with this video, pause wherever possible. So we'll just work it out this time and see whether it is working well with you guys or not. So what I intend to cover today is parallax, and then errors. Now, what is parallax? Many of you might be knowing it. Whenever you think you want to say something or you want to think about something, you just pause the video and then think about it and then continue the video. So it's not like you'll have to watch in one go. So if the recording is worth 1 hour, you'll be given 2 hours for it, so that you can work out along with the video, pause wherever it is required, rewind and watch whenever needed, but you'll have a limited window of time to do your work and then come for the live discussion of the stuff which is being taught right now. Now, to get distances, that to great distances where we cannot measure with a measuring tape or something, like suppose the distance from here to moon, from here to the nearest star in fact. So that kind of distances, to measure that, we use a method which is called parallax. Now what is that method? That depends on the vision. Suppose you are here, you are the person who is observing, this A is you, and you want to know how far is B, and you don't have a tape to measure it, you can't do it physically suppose, then you do something which is called parallax. And what is that? You look at B such that you have a reference of angle, at what angle you are looking at B. Suppose you are looking at B and you spot a very far off object. I hope that is coming in the, okay. Suppose this is the far off object C. Now I think you would have observed that if you are moving on a road, and you're observing a far off object, a very far off object, suppose the mountains, or in fact say the moon, then you always feel that the moon is following you. You're here, you're on the road, you're there, that's your moon. You've gone here and you feel moon is here. You don't think that moon has been left behind. It's not like you will travel 50 kilometers or 10 kilometers. Earlier the moon was here and you have traveled 10 kilometers and the moon is behind. That never happens. Moon is beside you and moon is always beside you. And in fact, when I was a child, I was always wondering what is happening, and it seems like it is coming behind me. So we know that the moon is there, and this phenomena most of us would have observed. I hope you would have observed. Moon is there, moon is still beside you, moon is still beside you, your dad is driving the car very fast, that doesn't matter. But if something which is nearby, say the trees, the tree which was beside you, once you have gone over here, the tree is behind you. Now this fact that a nearby object will angularly go back much faster than a far off object. So if there was so moon is say far off, we have a big board over here. So there were mountains and then moon is way away. This is a reference point. A sees the trees and A sees the mountain behind. Now A wants to know, after he has gone this much, how much angle has he gone back? Because if he is looking straight at the tree, and from here also he is looking straight at the tree, and he doesn't have a reference of the road, he doesn't know how much angle he has gone behind. I'll talk about that again, but then let me just make the drawing. Now he sees the tree and he sees the mountain. So roughly he says that this is horizontal. So with respect to his vision of the mountain right now and the tree, these two angles what he's seeing, straight and up. The angle here is roughly this angle, right? Because if this is parallel to that, if this is roughly parallel, this angle, I'll call it as theta dash, will be almost like theta if you're observing something which is way away. Like something else was here. And when you were looking at the tree, you kept that other thing, I'll call it as moon, but moon is much far away. So when you're looking at the tree and you kept the moon behind, the tree, straight behind the tree, and you made a straight line like that. And when you go ahead, then you look at the moon and you look at the tree. So the angle difference, looking at the moon and looking at the tree, that angle difference, this angle difference, I'll mark it with yellow now, say alpha. Will that be this angle almost or not? Since I've made a theta dash over here, I'll call it as theta double dash. Will this theta double dash be almost as theta dash or not? Yes, it will be, because now this blue line is almost parallel to the white line. So we have managed to get this angle. Once we have managed to get this angle, this distance of travel was obviously known, and that is called the base length or the basis. So I'll call it as B. So that base length you know, that theta angle you know. Do you know how far the tree was? So like sitting in the car, nobody is allowing you to go to the tree to measure how far it is. If you are doing enough of physics and math, I mean, it will be quite a job to get the angle, because you don't have an instrument in the car to get the angle. But suppose you can estimate that angle. With in physics, we have precise instrument to measure angles, very precise instrument. So we get that angle, we get one length. So in a right angle triangle, if you have one length, any one length, and the angle, you have all the other sides. So here, to get this distance x, we'll say tan theta is equal to b by x. Hence, your x is equal to b divided by tan theta. Got the point? So this thing, when we are observing something which is in front of us, you can do it with your finger right now. That is how it is written in most of the places, but obviously you will not measure the distance between your eye and the finger with this method. You can straight away measure it. But you close one of your eyes with your palm, look at the finger, and have something behind the finger fixed at the tip of the finger. Keep it in a straight line, and then open the other eye and the palm. Now what do you see? What do you see? The far off thing which you were seeing is still straight, but the finger has gone somewhere else. So that was, suppose, your finger, and that was the far off thing. With one eye, you're observing this and the far off thing. Now when you observe with the other eye, the far off thing is still straight, almost straight, and this has gone this side. So this phenomena is called parallax. You are utilizing this to get the distance, because you know the distance between your two eyes. That's called the basis. You know that base length. You somehow figure the angle. You figure the angle by doing the measurements using instruments to get the angle, like seeing straight, seeing there. So simple instruments which has two dots, two pins behind each other. You place the two pins, one behind the other. That's one length. And then when you place the pin over here, again see the two pins behind the other, that is another angle. So again, we are not talking about the instrument, because neither that is in course, and nor that is the point over here. The point over here is how do you get that distance between yourself and the thing what you are measuring. So I hope you got it with the tree. So what I was saying over here was, I was saying the same thing. So you'll rather practice a question with this, and you'll get to know what is happening over here. So I'll just talk about this parallax, which is how it is actually being utilized. Obviously, it is not being utilized to get the distance between yourself and the tree. You can always stop the car and get the distance, and maybe in a more accurate way. But then, how do you know the distance between the Earth and a certain star? How do you know that? How do you know the distance between Earth and a certain star? In fact, if I ask you, how do you know the distance between Earth and Sun? There were estimates, there were various ways of measuring, but then methods were right, estimates were wrong. That's a very, very cool history. You can go and read through it. And till very off late, we did not know the exact distance. You can say that it is one astronomical unit, 1 AU, astronomical is the average distance between Earth and the Sun, because Earth and Sun doesn't has a fixed distance, because the orbit of the Earth is elliptical, and it is roughly like 1.496, I guess it is written in the books, into 10 power 11 meters. So I'll just verify this number. Yeah, I think that's right. So that's the average distance between Earth and Sun. Why do you need such a large distance? If you have this distance between Earth and Sun, that's your Sun, this is your Earth, I'll make it blue. If you know this exactly, you can do some very cool celestial distances, like the distance between Sun and the next nearest star. So to do that distance, first of all, this distance has to be known properly. Now why do I say that? Suppose you want to know. Yeah, so what I was saying is, how do you know this? You read yourself, it is not in course, it is a good read, but you read yourself. Well, how do you know the distance between Earth and Sun? There are various ways, very, very cool ways. Like if Mercury is passing the Sun, then that Mercury is having a certain dot in this, in front of the burning sphere, and I mean very off late till 1900 something, you can actually see that dot going through. You have your estimates of how Mercury, what is the speed of Mercury or how far is the Mercury and all. Everything is interlinked, and you can somehow get the die of the sun. So there are various methods applied to get the distance of the sun. Various methods applied to get the distance of the sun. Die of the sun, again you'll do the parallax and can get it. Now, if you know this, how do you know this? You read parallax is, if you know this, then suppose I want to estimate the distance of a certain star, a nearby star. So there are some stars, when you observe in the sky, after a month or two, you will feel that it has gone a slight angular distance. You can't feel after a month or two, I'm sorry about that. But when you are observing it and you have a map, you have mapped the star, say this is your sky. In a certain month, you observe the sky, lot of stars. I'll call these as far off stars. And you are observing a star which is a nearby star. I know why it is nearby star, because after a month, this star seems to be here, and the rest of the star is where they were. The rest of the star are where they were. So the rest of the star are where they were after a month, and this star seems to have moved. It is same as your parallax. You are observing the tree, and this behind thing is the rest of the stars, which are far, far away. This is the nearby star. When you go over there, then the far thing still looks the same. That you can see right now, putting your finger in front and seeing the scene behind, something which is far off. Okay, don't look at the wall which is quite nearby to you, something which is far off. Okay, at least some 5-6 meters away at least, and then watch your finger with one eye and then the other eye. So the behind scene is the same, but the front scene, the forward scene has changed. So that is your parallax. The behind thing remains same, and you're here. The C is still over there for you, but the B has gone back. So if you observe that angle, how much it has gone back, you can estimate how far it is. So you map the sky should look the same, and then the star which has shifted is the star whose distance you are going to measure by parallax. So let me just make the drawing over here, and let us have, as I was saying, if you have a good base length, like this much, you have gone from here to there, then this angle, the angular shift, this theta roughly to that theta, this angular shift would be much greater, right? If you have gone larger distance. Meaning to say, if I have to observe the parallax in the star, I can't use my two eyes to do it, right? I'll hardly have any difference in that. In fact, if I'm observing something just a meter away from me and I use the two eyes, you can just do that. Okay, something which is 4 meters away, use the first eye, watch it, close the first eye, use the second eye and watch that. Has it shifted? It has not shifted. But if something is as near as this, use one eye and use the other eye, it shifts a lot, right? So the point is, if you are observing, it is all relative. If you are observing something which is far away, like if I am observing the thing which was 3 meters away, I have to move some meters to see a shift between that thing and the scene behind. Now this scene behind is a reference of the angle, because if you have no other reference, imagine a world. I can't just demonstrate over here because nobody's here. Imagine a place where just it is deep sky, you and a certain object. You look at the object B. You are looking, A is looking at B. Now you close your eyes. You are rotating and all. You close your eyes. Suppose you are here. Some God knows that you are here. But then from here you look at B. How do you know that you have gone somewhere else? B was there somewhere in front of you. After a while, B is there still in front of you. You don't know that you have rotated and all. B is there in front of you. How do you know that you have gone a certain distance? You don't know that. You don't know that unless until there is a reference of something which is far away. If something which is nearby, near to C, again you don't know that. You are seeing A and B in front of you. Now you are here, you are seeing A and B in front of you. Slight difference in the way they look, but you don't know how far it is for good. Now, if something is far, far away, which acts as a scene, when you have gone over here, that scene doesn't change. That scene seems same. So that is your reference. And then you feel that the B has gone back. Instead of B being front, B was in front. You will feel that B should have been here and B has gone back. You still don't feel that you have gone forward. You feel that the B has gone back because the behind scene is same. So the point what I was making is, larger is this distance. Greater distances of U and B, the distance between U and B can be measured. Like the distance between the two eyes is very less. So I can observe the parallax with fingers which are nearby, with finger which is nearby. If I shift so much from here to there, I can observe parallax in things which are, you can shift your head and see, okay? So, which are a little far. So stars are way, way away. If I take one astronomical unit as a great and good distance, then the star would be like lakhs and lakhs of astronomical unit away. So this is of no use measuring the distance between celestial bodies, apart from measuring the distance within the solar system, that's okay. But then this value was a big deal. To get the value right, you can say that light takes 8 minutes to come to you, but how do you know it takes 8 minutes? How do you know what is the distance? It was a very, very big deal to get the distance between the sun and earth. Till late, we didn't have an exact figure. And we wanted to know that figure exactly because that becomes the base length, or that becomes the basis of measuring other distances. So if that is wrong, other distances would be wrong. So what is it? Suppose there is a star here which you want to measure, and that far, far away is the rest of the stars. The rest of the stars, you can see the galaxy, you can see it. There's a complication here, by the way. The behind scene has to be seen, and the earth keeps on rotating. The earth keeps on rotating, so the behind scene keeps changing. So you have to either wait for the time such that the behind scene is same. After 1 month when you are observing, or after a few months when you are observing, you have to wait for the time such that the behind scene is same, or you go to the place such that the behind scene is same as your first observation, and that is like within 24 hours the earth rotates a whole round, so you can get the scene same. So I'm not making the behind scene, and then you look at the star, right? You look at the scene behind and you look at the star. Just for convenience, I'm going to make a star which is, I can't make it, it is like way, way behind other stars. If this is 1, then the other stars are hundreds and hundreds of units away if this is 1. Okay, thousands of units away in fact. So looking behind gives you a straight line. Looking at the star gives you an angle, and you measure that angle. You wait for 6 months. Why do you wait for 6 months? So that you get the largest basis possible living on earth. It is not the distance between the two eyes, it is distance from here to there. It's not the distance between when you're looking at the tree from one place in the car to the other place in the car. Not that distance, but a much greater distance. So you wait for 6 months, and the earth is here. Now again, when you see the scene behind, that again makes your straight line, because the behind scene doesn't change, because this distance is hardly anything with respect to the distance of the far, far away stars. So you don't feel that you have gone anywhere. You don't feel you have moved so much. What you feel is this thing has gone back by how much? By this angle. Get the point? Get the point? If this star was right at the center, both the angles are going to come same. So what they do is they observe after 3 months also, and they observe this straight line also. The straight line behind, I mean, they have ways of knowing that it is a straight line. The sun is behind and that is in front. You can do that. Otherwise, you are from here to here, you are observing that, you'll have to do little more math. So this is a very simple math what we are trying to do. And to ensure that this is what is happening, you have to observe accordingly. Not a big deal. Not a big deal in doing this, because this was being done way, way long back. The problem was you don't have a good measurement of the distance, hence the other answers were also a bit off, quite a bit off. So once you get these angles, you have got the whole angle. This is your 2 theta, right? You know the distance between sun and earth, that is your 1 AU. That's your 1 AU. Now either you can take the whole arc length, this length, and 2 theta, or you know this is a right angle triangle. Both math is going to give you the same thing. We are going to just discuss the math over here. So for now, I'll just say that this is theta, this is AU. How much will this length come as? So you will say tan theta is equal to 1 AU divided by x. Hence, x is equal to 1 AU divided by tan theta. Got the point? Okay, one thing I just skipped in the start. One basic thing what you need to know is what is the relation between angle and radius and the arc length. For our physics, we have to know only two basic things, very basic things. What is that? This is just by definition. Angle radians, radians is defined like that. 1 radian, 1 radian is the angle when your radius is equal to the arc length. If radius is equal, you make any radius, you make a radius of 2 or 10 or 5 and the same arc, then this angle will be a special angle. It will be roughly, can you tell me, think yourself and tell me, this angle will be near to 60, more than 60 or less than 60. Don't do a back calculation, just by geometry, think and tell me what will it be. So pause the video, think, pause, because I'll speak out the answer. The question is, 1 radian is roughly, it's nearby 60, I can tell you that. Is it slightly more than 60 or slightly less than 60? That's the question. So pause. Now suppose you have resumed the video, then this is the answer. If I think of an equilateral triangle, 60, 60, 60 degree, this is R, that is R, right? So how much is the arc length? How much is this arc length? That arc length, white length would be slightly more than R because the straight line was R. Arc length will be more than R. What did I say over here? I said the arc length is R. If the arc length is R, then this should be greater than 60 or less than 60. So this arc length is greater than R. So to make the arc length equal to R, if the arc length is equal to R, so it ends somewhere over here. This arc length, white length is greater than R. So arc length equal to R will end somewhere over here. So from there to there, if I join, this is your 1 radian. Get the point? And obviously we'll be doing the math. So and get the exact value. So by the way, 1 radian is when the arc length is equal to R. So half a radian will be what? When the arc length is half of that of R, right? So theta radians will be what? Theta times R, or theta radians will be L by R. The arc length by R. If theta radian was 1, it is R by R. If theta radian is half, it is R by 2. The arc length becomes, if it is half, the arc length becomes R by 2. It is simple unitary method. Simple unitary method. Hence, what we can say is arc length L is equal to R times theta. Remember it for the next 2 years, because this is like basic, very basic as A into B is your area. These two will be coming again and again, and there is no explanation to it. A into B is the area. Okay, that is the area. You can imagine A times B is drawn, and you can call it as an area, whatever. Similarly over here, theta has been defined like that arc length is equal to radius times theta. If theta is in radians, by the way, theta is in radians. Okay, now I hope you know 180 degrees pi radians. This is R. So how much is the arc length? Arc length will be theta times R, which is pi R. So the camera went off, I don't know where, somewhere around when I was telling you what is arc length. So pi is the angle, R is the radius. So your arc length would be R times pi. So pi R is your arc length for pi angle. Hence circumference of a circle is 2 pi R. Okay. Now for very small angles, your sine theta or tan theta is almost equal to theta. That is what we consider for very small angles. And if you use your calculators, you can punch in some angles in radians, which is say between 1 and 4 degrees, and you'll see that the answer is right. Okay, so first you should know what is the conversion between degrees and radians. So I'll just give you a conversion between degrees and radians. Pi is a number, mind you. Pi is a number. Pi is like 3.14 something is a number. Now, yeah, 180 degree is pi radians. So what will be 1 degree? 1 degree will be pi by 180 radians. Hence, your theta in degrees will be pi by 180 into theta radians. I hope this has been done in math already. In the math class, they have started with trigonometry, so I don't have to tell you more. Now, very small angles, degree is a big angle when you are doing all this stuff. So for very small angles, because mind you, what I have drawn, no star is nearby here. It seems nearer than your Venus. That's impossible. The star is way away. So this angle is way small. Couldn't have drawn on the board. So these angles are quite small angles. Okay. So if you split up a theta, they don't split it up in 100 parts or 10 parts. It's not a decimal system. So it is split in 60 parts. So those are called minutes, and those are further split into 60 parts, and those are called seconds. So minutes symbol is a single dash, second it is a double dash. So if I say 2 degrees 40 minute and say 20 seconds, what is the angle in degrees alone? First of all, what is the angle in degrees alone? 2 plus how many degrees over here? It's a 40 by 60 degrees over here. 2 degree plus 40 by 60 degree. Then 20 minutes is how many? 20 seconds is how many minutes? It is 20 by 60 minutes. 20 by 60 minutes, which is again a 1 by 60 of that will be the degrees. So it is same as your time. It is like 2 hours 40 minutes 20 seconds. How many hours? It is 2 hours 40 by 60 hours and 20 by 3600 hours. So first you convert everything to degrees, and then how many radians it will be? Into pi by 180. You can always remember that it has to be way low radians. 3 point something is 3 point something radian, 3.14 radian is 180 degree. So 1 degree will be 3.14 chopped into 180 parts. Okay. So if you have x seconds, how many radians will it be? First of all, x seconds would be x by 3600 degrees, and that into pi by 180 radians. So x seconds will be so much degrees. Sorry, I'm so sorry. So much radians. Got the point? Got the point? So you'll be getting a lot of minutes and degrees over here. Okay. Now bases, either this is a good base, this is the biggest base we can do. But if suppose we have to observe moon, then on Earth we can go from one end of the Earth to the diametrically opposite end of the Earth and observe moon. This dia of Earth itself can serve a good basis, and then they will give you the angle what they have observed. It was so much up, it was so much down, maybe these two angles they are saying, and you get a 2 theta. Get the point? Now if this angle is very low, then we'll come to this point that sine theta is almost theta, tan theta is almost theta. How does it help? Again, that is a thing which is being used again and again and again. What part shall I rub off? Okay. Yeah. Let me make a triangle with a low angle, but I'm talking of angles which are much lower than this also. Okay. If this much is your 30 degree, this much is roughly a 30 degree, then I have made a 10 degree, slightly less than 10 degree, but not low enough for what I'm talking. And if I go, I mean, you can still roughly estimate this for these angles also, for 10 degrees also. For our rough estimations, particularly in JEE, when you have objective answers and you have to choose from one, you don't have to be exact, precise on your calculation at times, because the other options are far away. If they are very near, then you can't do. But then they are not testing your calculations, so they are testing your concept. So this, for even 10 degrees you can apply this, okay, but it is obviously for measuring the distance you can't do that kind of error. You have to be exact till the seconds, and maybe further for measuring if you are doing the, if somebody is doing the celestial body distances, because there it is going to matter a lot. So precision is what is going to be next after this. If precision is high, our calculations are better. Anyways, so what was I saying? This theta, suppose your, I'll call this as, I'll not use the letter B over here. So say P is for perpendicular, what the hell? Say X, Y, Z, yeah, easiest. Now, what is sine theta? Sine theta is equal to Y by Z, right? Right? Get the point? So what is your Y over here? How much is your Y over here according to sine theta? Y is equal to Z sine theta. Now what is tan theta? Tan theta is Y by X. So what is Y? X tan theta. And this thing, what did I say? If you have an arc of say Z or X, which one shall I make? Which one shall I make? I'll make only one. Say of Z I make, and I go over here. It is cutting my Y, so I'll just make an arc of X, so that X is my arc is my radius, and I make an arc of X, and I cut over here. I'll call this yellow length as Y dash. According to this, which is absolutely precise, radius times angle is your arc length, radius times angle is your arc length, what do I get? I get this arc length y dash is the radius, which was x times the angle theta, right? And if I make, I'll just do it whether it cuts my y or not. I'll make an arc length with z and I'll get that. That's my y double dash. Y double dash is equal to z times theta. Now can you see why I was saying this? Theta is almost equal to sin theta, theta is almost equal to tan theta for small angles. Can you see these relations? Pause the video and see. Pause the video and see. For very small angles, your x will be almost equal to z. X is almost equal to z because the angle is too small. The angle is too small. This orange one, if you can see in the video, that kind of angle we are talking. So x and z are almost the same thing. And then where that angle meets over here, your y dash or the perpendicular is almost the same thing. Y double dash and y almost the same thing. Get the point? So if your y double dash or y is almost the same thing, then your y was coming as x tan theta. That means it is x times theta, right? That means tan theta must be equal to theta, almost equal to theta. Are you getting the point? Look over here very closely, which concludes that I'll just write one of them. All four might confuse you. I'll just write one of them. Y is equal to x tan theta, and it is almost equal to y is, according to that, y is almost equal to x times theta. The arc length is x times theta. So x theta almost equal to that. Y is x tan theta. These are exact calculations. These are almost equal. This one is almost equal. So y is almost equal to y dash, which is x theta. Meaning to say what? Meaning to say tan theta is almost equal to theta. Similarly, you can pick up the z wala thing, this and this, and show they are almost same. Okay, so for small angles, you need not go to the trigonometric table and find out the sine and tan theta value. You'll get it to the right decimal places. Even if you're going to the 4th or 5th decimal place, you'll get it right. So in the table itself, you have a limitation of 4 decimal places, so it is not going to help you anyhow. Got the point? Okay, so do some questions. Do some questions. I'll read out a question. I'll share the NCERT book with you, and then you have 4 solved examples. You do all of them with your own hand, and just let me read one question for you right now. That is example number 2.2. Do not look at the solution at all and you solve. I'll just read it fast. You can pause and rewind again and again. A man wishes to estimate the distance of a nearby tower from him. He stands at a point A in front of the tower C. The tower is C. He stands at a point A in front of the tower. The tower is C, and spots a very distant object O in line with AC. He spots a distant object O in line with AC. He then walks perpendicular to AC. So he has seen an AC line. Now he is walking perpendicular to AC. What will happen? What will happen? The C will lag behind. So he walks up to a point B. So I'll repeat the line. He then walks perpendicular to AC up to B, comma, a distance of 100 meters. That means from A to B, the distance is 100 meters, and looks at O and C again. So O was distant. O will still look the same for him, but the C will look behind, right? It will seem to have gone behind, right? So, and looks at O and C again, full stop. Since O is very distant, the direction of BO is practically the same. The direction of BO is practically the same as AO, but he finds that the line of sight of C shifted from the original line of sight by an angle theta. So mark the theta correctly over here. The thetas can be different things, okay? So like from here to here, the theta was here 2 theta. So if I use 2AU as the arc length, 2AU as the arc length, then this length into 2 theta is your arc length, and hence I'll get that length. If I use theta, then I'm talking about this triangle. So be careful what triangle or what arc we are talking about. Okay. From the original line of sight, I'll just repeat. He finds the line of sight of C shifted from the original line of sight by an angle theta is equal to 40 degrees. That's a big shift. Theta is known as parallax, is given over here. Estimate the distance of tower C from the original position A. Estimate the distance of the tower C from the original position A. So make a good drawing, make use of these facts, what has been given to you, and get the answer. And then what you do is solve the other three examples given in NCERT, which I'm going to share right now. No, when you come for the class at 7, I'm going to share it. and then rest also is a very interesting reading, and you can do that once you have done with these questions. One thing I did not tell you over here is the unit parsec. 1 parsec. Now, AU, astronomical unit, seems to be very, very small when you are studying the distance between the stars. By the way, if you are studying the distance, if you got the distance of one of the bright star which is nearby, how to get another star which is way far off? How to get that distance? Know what they use? So the sky behind it, yes, there is sky behind it. If you have a very powerful telescope, you might be able to see that, but the parallax angle will come very, very low, and the estimation may not be that good. So how do you estimate is by the brightness difference, by how much bright that star is compared to this star. So once you have got this distance, which was based on AU, so hence AU was a big deal. You get the AU right, you get this distance right, you get this distance right, you get the far off distance right. So if it is estimated that both are same size stars, if it is known that both are same brightness star, if they were one beside the other, then comparing the brightness tells you how far that is, okay, with some precise physics and math over there. Now, how do you know that they were of the same intensity? They study the spectrum from the star and then they estimate that, okay. So a lot of things in astronomy, if you guys are interested, it will require some deep math and very cool stuff. So what was I saying? Parsec. Parsec is a big unit, 3.08. Parsec is the unit in which you can actually get the distance of stars from Earth to Sun, which is the nearest star, which is way less, is 1 AU, is way less. 1.08 into 10 power 16 meters. So that was 10 power 11. So you have a 10 power 5 difference. Okay, so it is like million more. So this parsec, how do you get that parsec? When you have a parallax angle of 1 second, 1 second parallax angle with a AU, with the basis as AU, the base length as AU. If you get 1 second, then the distance which comes, if this theta is 1 second, then the distance which comes is called 1 parsec, parallax second. The name has come from there. Okay. So I'll just stop this video and start with errors while you do the work which has been given to you. Thank you.